You're listening to WMPG 90.9 Gorham Portland Sun Main Community Radio from USM. Live from the Orion Cygnus arm of the Milky Way galaxy, this is Scientifically Speaking, a weekly half-hour program devoted to elegant curiosities, and I am one of your hosts, Sarah Chang, and joining me as always is Bernie Rhyme, DJ Star Watcher. How are you, Bernie?
Yes, hi Sarah, very good, thank you.
Bernie is our professor of the astronomy lab here at USM and our local protector of the night skies. Reach out to us at WMPGScientificallySpeaking at gmail.com or on Twitter at WMPGSciSpeak, and you can head over to WMPG.org to find the last 5 weeks of archives of all of your favorite shows, including this one. Bernie, could you let our listeners know what is up in the night sky for this coming week?
Oh, certainly. Okay, so this will be Friday, February 4th. So we're going to have a waning crescent moon. It was actually new just a couple days ago on the 2nd. The waxing crescent moon. So the waxing crescent is the best phase because it's getting a little bit bigger. You can see the Earth shine on it, then it disappears an hour or two after sunset. So then you get a nice clear sky if it is clear, and you can see that without the moon in the way. And the best time to look at the moon too is when it's crescent, even if you're going to magnify it, because then you can see the terminator line and of course the Earth shine like I mentioned and so on. Okay, so the days have finally reached 10 hours long. So that was a while since the solstice. So the sun rises at 6:54 and sets at 4:55. So it's 10 hours and 1 minute. So it's very noticeable now. It was kind of a little bit noticeable already in January, but it's obviously now it's February, so the sun is getting a lot stronger and higher. So that's good. So planet-wise, we still only have Jupiter left in the evening sky, but everything else is pretty much in the morning sky. Mars and Venus will be fairly close. Saturn will join him, and in a few weeks, even you can see Mercury for a couple of weeks in the morning sky later on in February. So we have a lot of things going on in the morning sky then.
Yeah. Excellent. Yeah, it's so exciting to get more light.
Yeah, I know. 10 hours is a big thing. Yeah. Yeah. Mm-hmm.
Awesome.
Yeah.
Thank you, Bernie.
Yeah, you're welcome.
And if you could not take notes fast enough, you can also check out the monthly What's Up column in the Portland Press Herald. So welcome to another episode of Scientifically Speaking here in WMPG. And today we are going to go through some FAQs on astronomy. And so we collected a couple of questions from various sources, some from listeners, some not. And we compiled a list that we thought were interesting and that other listeners that we have would find equally interesting. And so we're going to go through this list and just try to go through these questions and get more of the science out there to you listeners here in Maine and possibly anywhere else that is listening. Let us know if you're listening from not in Maine, by the way.
Yeah, hopefully some people are.
Yeah. All right, so Bernie is our resident astronomer, and I'm just here to help out. But the first question that is up on the docket is, and I think this is a popular one. We've seen it in movies, portrayed in movies, but thought this was a very good question. So if we could travel at close to the speed of light, it would take about 4 years to get to Alpha Centauri. Would the people on the spaceship feel like they were stuck on board for 4 years, or would it feel shorter for them, or something different?
Mm-hmm. Yeah. Yes. Well, this is kind of getting into the whole Einstein twin paradox, which is really interesting and goes way beyond just that one example. Almost like a math formula will go beyond any one particular set of numbers you could plug in. So basically those people would feel like it's 4 years. Biologically, it would be 4 years for them. So they'd hopefully have something interesting to do or whatever. However, the thing is now, because they're going, it's called relativistic speed. Anything over 99 point some percent the speed of light is called relativistic when these effects really take over. So for them, they would age to 4 years, but once they come back, say in 8 years, say if they were 20 years old when they left, and then they come back, and they would be 28, considering they're going both ways, and then their twin here would be like 78 or 80, or just about at the end of their life. And the reason is, if you're moving faster through space, even though for yourself you're aging at the same rate, in relation to that reference frame of the people on Earth who aren't just, I mean, we're moving a little bit through space, but nowhere the fraction of the speed of light, that the time would go a lot slower. So that's why, once they come back, their twin would be really old. So it's neat though, because then you can go to these other places in just about the time. So 4 light years away, you can get there in just over 4 years, say maybe 5 years or something. But the problem is when you get back with any information or knowledge, or if you do want to come back, then everybody is just about at the end of their life, and you're only 5 to 10 years older. Yeah.
Mm.
So that.
I heard that very explanation of like the twin.
Mm-hmm.
Um, and it's like I get it,
Mm-hmm.
but like
Mm-hmm.
why are there two different timelines?
Oh well, that happens all the time. Actually, no, that's a good question, and they can do this with molecules. I can tell you lots of neat ways. You can actually do it with muons. These are a second cousin to
Mm.
the electron. They're about 2,000 times heavier. They're extremely short-lived. They live 22 microseconds. So if they come in through the atmosphere, they come from cosmic rays. So they have to go through 15 kilometers of atmosphere, and you would think they would get only about 600 meters in that time. However, you get about 1 per second that makes it all the way to the surface of the Earth. And we can have measurements. We can look at these muons. So that time dilation is going on with the muons because they can make it through 15 kilometers in 22 microseconds, which they could never do
Mm.
if they weren't actually have the relativistic thing and live longer than they would actually live. So we can do it with particles. Obviously, we haven't done it with spaceships or humans or anything living or a
Right.
plant and an animal, but we can do it with particles all day long. So that happens all the time. And time actually is really interesting too because time actually flows. There's two ways to do this. You can travel near the speed of light, or there's another way you can time shift like that. You can go near a strong gravitational source like a black hole. So that's what the movie
Mm.
Interstellar is all about. I mean, that black hole was near Saturn. Of course, we don't have any black holes within probably 5,000 light years of us, which is a good thing. So even near the center of the Earth, because you have more, the gravity there, time flows a little bit slower than it does a little further out. It's only like a picosecond, which is a trillionth of a second. But even a couple of millimeters difference, and this is actually one of the big science stories of last year that I don't think we covered this. We have atomic clocks precise enough to measure a different flow of time 1 millimeter further off the surface of the Earth than 1 millimeter closer to the Earth. Now, in the case of the
Mm.
Earth, it's not a big deal, but when you get a near black hole, if you stay there for like 7 hours, that's the equivalent of about 50 years on the Earth. So Matt McConaughey was near the black hole for 7 hours, and his daughter became older than he was. And that was
Mm.
pretty accurate, precisely done. Except we can't do it with living people. We can do it with atoms and molecules and stuff like that right now.
Yeah.
So
Hmm.
that's how it works. Yeah.
Interesting.
Mm-hmm.
All right. Next question
Mm-hmm.
from my list.
Mm-hmm.
Is it at all possible for a planet's moon to be gaseous?
Mm-hmm.
So I think maybe we mean like a gas giant, kind of like
Jupiter or Saturn.
Neptune is a gas. Yeah.
Yeah.
Is Neptune?
Yeah, we have four
Neptune
gas
is.
planets: Jupiter,
Yeah.
Saturn, Uranus, and Neptune. Yep.
Yes.
Yeah.
I
Yeah.
think the answer is probably.
Mm-hmm.
Um, and this isn't a very long answer, but there is at least one candidate moon discovered by extrasolar planet hunters called Kepler 1625b. And it is possibly about the same size of Neptune, and it orbits a planet about the same radius as Jupiter, but about 10 times the mass.
Mm-hmm.
So, probably is the answer to that.
Yeah. Because even the center of Jupiter might not be solid at all. It could be like a liquid hydrogen at the center of
Mm,
Jupiter. So, I mean, it's certainly
mm,
not a gas because Jupiter basically is all gas until it just gets really dense at the center. And they don't really know what it is, but it could be just liquid metallic hydrogen, which is pretty neat stuff too.
yeah.
Yeah. So a moon could be
All
that.
right. My third question, and then we'll shift over to you.
Mm-hmm.
And this is related to James Webb. So the question is, could the Hubble and the James Webb telescope take a photo of one another? So telescope and instrumentation on the James Webb telescope have to be kept at these super cool temperatures. You were just talking about some temperatures in
Yeah,
one of our previous
328
shows.
below zero. This was like a few weeks before this will air. There's actual temperatures given on the website where you can update where the web is. So
Mhm.
the cold side was minus 328. It has to get colder for that for the infrared to work. And the hot side was 130 degrees. So even though
Mm.
we're almost a million miles out in space now, it's 130 degrees. So you can tell how powerful the sun is even at that distance.
Yeah, yeah.
Yeah.
Um, yeah, so there's two parts to this question. One is the physical part of it of like, is it physically capable of doing this? So there's this huge sun shield on the James Webb Telescope, and the Earth sits between the sun and the James Webb Telescope. And so if the James Webb Telescope wanted to image something in Earth's orbit, it would have to turn to face both the Earth and the sun, thereby causing temperatures on the telescope
Yeah.
to rise by a lot,
Yeah.
like a ton,
Yeah.
causing it to then
Yeah.
malfunction.
So it would.
So that's one
Yeah.
that's one issue. The second issue, I think, is the distance between the James Webb Telescope and the Hubble is about a million miles,
Yeah.
and the relatively small size of each of them. I think the Hubble is what, 40 feet. James Webb is 60 feet.
Yeah.
Um, at its most expanded size, is kind of like trying to take a photograph of the tiniest like needle pin in a football field
Hmm.
from like the nosebleed seats.
Yeah.
And so just the optics of it
Hmm.
won't work.
Yeah.
So anyway, so two answers. Two answers
Yeah.
there.
Right. Yeah, and even
All
the
right.
Hubble is only made to take pictures up above it. It's not made to look back at the Earth like a spy satellite would be.
Yeah. Yeah.
So
Yeah.
yeah, yeah,
All right.
mhm.
I think one of your questions, Bernie,
Yeah,
is why is the speed of light what it is?
yes, right. So that is an interesting question. It actually give you some insights into the very nature of the universe and the vacuum and where we live and all kinds of neat things. So you know the speed, of course, is 186,000 miles per second or 300,000 kilometers per second, if you think metric, and that's fine. Some people do. Um, so yes, so actually that number by itself isn't all that important because it's kind of man-made arbitrary units based on
Mm,
the time factor. Time it just obviously it's based on the sun going
right.
around the Earth going
Right.
around the sun, and then the speed could be miles or meters, and that's kind of
Could be any
arbitrary.
unit. Right.
Yeah, a meter is actually based on the speed of light, so it's almost like a self-reflecting. It's 1/10 millionth of the distance from the North Pole to the equator. It's defined as a meter, but that's also
Right.
based on a fraction of
Right.
the speed of light.
Yeah. And we
So
could base everything on one being the speed of light,
yeah,
technically.
yeah, right, exactly. So the number per se doesn't matter. However, it is that number for a very important reason, and this is huge if you never thought about like the nature of space-time itself. So what that number is, without getting into the equation and the formula, then you could actually figure this out yourself if you knew a few things like Planck's constant and so on. So it's actually based on the permittivity of free space,
Mm,
like how free space would conduct this. Because remember, light is a self-propagating electromagnetic wave. Okay, so you can never add to that speed, and you can never subtract from it. And this was a huge thing. It's the whole basis of special relativity in 1905. So you can't put a
mm,
flashlight on a train, and if it's coming towards you, you think it's going the speed of light plus 60. Or if the train's
mm,
going away from you, you think it's going the speed of light minus 60. That's not the case.
mm,
It's always going at the speed of light. So that by
mm,
itself, if you never thought of it, that's a huge mystery. How can it still be at the speed of light if it's going away from, even if it's going away from you at 99.9% the speed of light, it's still going to hit you at the speed of light. So
mm,
that's really interesting stuff. Okay. So of course, for that to be the case, because light is always constant, it is that speed. And I'll tell you in a minute why it's that speed. So then the whole breakthrough of relativity is that then time and space have to be flexible. So time can
mm,
change, as we just talked about in the other question with the Einstein twin paradox. Two ways you can change it. You can move really fast, or you can get close to a gravitational source. And space is also flexible because time is kind of the other side of space. You can think of light as kind of connecting or correlating the two, time and space. So they're kind of connected with the speed of light. So that has to be constant. And the reason it is that number, and it could be a different number in a different universe and everything, but it's very constant throughout the whole known universe, the whole 100 billion light year diameter of our known universe. And that is based on the permittivity of free space, the vacuum to do this, and the permeability of the vacuum to hold a magnetic field. Because remember, light is two things leapfrogging. It's electric and magnetism based on Maxwell's equations. So it's electromagnetic wave that just propagates itself all the time at that speed. And of course, this is in a vacuum. Of course, we can slow down light and you can go through water and we can slow it down to walking speed in the lab and all that. But the light in a vacuum, based on the vacuum of this universe, that's the speed and that's the reason for it.
Mm.
Yeah.
Interesting.
Yeah.
So we learned two vocab words, permittivity and permeability.
Yep. Yeah.
Awesome.
So it gets a little technical. I won't get into the equation. I had put them on the board for my students, but I don't have all the different constants to plug in. And that's not really the point. I think the point is that the number's arbitrary, but it tells us very something profound about the whole nature of our universe. There really is no vacuum. You can take all the molecules and atoms and photons out of a cubic centimeter space, and you're still going to have this. It's called the quantum foam. It gets into really neat stuff. You get virtual particles appearing and disappearing all the time. When they hit enough energy to pop out of the quantum foam, incredible things going on. And the speed of light is based on all that. Yeah.
Wow. It sounds like there's like a party going up in that.
Oh yeah, I know exactly.
There.
There's a constant party, and we can never see it. We see like maybe one. If in a lab, I think you get maybe one every second. It's very few things that pop into existence, and then they disappear right away with the antiparticle. And they give you a tiny burst of gamma ray light. But where they really come from, that's the really interesting thing, the quantum foam.
Yeah.
Yeah.
Cool.
Yep.
All right. Next question
Okay.
I got on the lineup is,
Yep.
can a planet, Bernie, be physically larger than its home star?
Well, I'm not sure. I didn't look into that answer because that.
I don't know. I was just pausing.
Oh yeah. Well, I don't know. I didn't look into it. I suppose it could be larger.
So,
Have some red dwarf. You have some white dwarf stars,
right.
and a white dwarf star is about the size of the Earth. And if you have a bigger than Earth planet, it could be orbiting a dead white dwarf star. So it could be bigger, sure.
So the answer that I kind of came up with is planets can get about as big as Jupiter, no matter the mass. And this is just because as mass increases, their gravity compresses the atmosphere more and more, leaving their size about the same, actually. It can become denser, but generally not larger in size. And so some of the smallest stars, objects that can sustain fusion, you just mentioned those were red dwarfs. And some of the smallest of them are about a tenth of the sun's diameter. And if we kind of compare that to the size of Jupiter, Jupiter is also about a tenth of the sun's radius.
Right.
So maybe it's possibly that it would be about the same, about the same size.
Yeah.
But being vastly bigger than their host star isn't really possible because then they would just probably be stars themselves. So, yeah, I think that's the answer there. All right, Bernie, here's one for you. How fast does the Earth rotate?
Okay. So that's a good question because it rotates at different speeds based on your latitude. So that's a really interesting thing. Of course, at the equator, it's pretty easy to figure out because we know it's about 25,000 miles in circumference, and we know there's 24 hours in a day. So at the equator, it rotates at 1,042 miles per hour. So that's easy. And it's actually kind of interesting because you would actually weigh less at the equator. So not it would only like be a pound or half a pound, but you would weigh less then.
Yeah.
And at the poles, it doesn't rotate at all. And then at our latitude, we're about halfway from the equator to the North Pole. So you would think that we rotate at 500 miles an hour, but it's not. It's actually faster because you have to take some trigonometry and some spherical surface, and there's really interesting stuff going on with the Earth. You can't just take half. But it's slightly different at every latitude. And for us, it's about 750 miles an hour, which is about the speed of sound. So that's kind of good to know. At this latitude, halfway equator to North Pole, we rotate at 750 miles an hour.
Hmm. Is there a minimum rotation speed?
Well, yeah, zero at the poles. Yeah,
But I mean, at the equator, like for the equator, is there
well,
some kind of
it's
like
a
what
thousand.
determines the speed that the like why is it rotating at that speed?
Okay, well, I mean, it was rotating a lot faster when the Earth first formed.
Mm,
It's slowing down due to a little bit of friction. There's gravity from the moon being
mm,
exerted on the Earth, a little bit friction with the atmosphere and the water
mm,
on the planet and so on. And yeah, it was one day used to last about 6 hours,
mm,
and now it's 24 hours.
mm,
So yeah, so the Earth rotation is slowing down. And if something would head to the center of the Earth really quick, like a giant underwater fall that would cause a tsunami, like angular momentum, a skater pulling their arms in, we actually sped up by a millisecond during that big earthquake in Indonesia. I think it was 2004, whenever it was. We sped
mm,
up a little bit just based on that little motion. But overall, we're slowing down about a millisecond per century or something. I mean, it's a
mm.
tiny amount, but over the 4.5 billion year history, from 6 hours, we're now at 24 hours, just about.
Interesting. Do you
Yeah.
know about the other planets in our solar system? Like, where do we fall in terms of
Mhm. Okay, good
rotation
question.
rate?
Jupiter and Saturn rotate much faster. They're
Mm,
10 times bigger, like you said.
mhm,
And one day on Jupiter is only 10 hours.
mm.
So it rotates really fast. So that's why you have all these built in storms and all the energy for the giant hurricanes like the red spots. And Mercury and Venus rotate really slow.
Hmm.
A day on Mercury a year is 88 days. A day is 259 days. So it's a 3-to-2
So
ratio.
its day is longer than its year.
Yeah. Yeah, and Venus is even more impressive. Venus, the year is 225 days, the day is 243. So Venus physically rotates at 4 miles an hour. So we can
Wow.
walk faster than Venus rotates. Super slow. And it rotates at record
Why?
rate.
Why do they rotate so slow? Is it because of their proximity to the sun?
Yeah, they're close to the sun. The sun is very strong. They don't have any moons for the same reason. The sun's
Hmm.
gravity field is so strong they can't hold on to any moons, and they rotate really slow.
Hmm.
And the Earth is a perfect distance, about 1,000 miles an hour, and then much faster when you go out further.
Hmm.
Yeah,
Interesting.
yeah.
And so, from the sun's perspective,
Mhm.
does if we were on the sun, could we see these planets rotating?
Um, yeah, they're not gravitationally locked. Like the Earth Moon is locked,
Okay.
so we only see the same
Yeah,
side.
yeah,
So they're
yeah.
not locked. But there
Hmm.
are some resonances actually, and Mercury's really interesting. Its whole orbit precesses.
Hmm.
And Newton kind of knew that, but Einstein gave the exact number. I think it's 0.043 degrees per year or something.
Hmm.
So he gave the exact number. It was about half the amount that Newton thought. And that was based on relativity, which we talked a little bit about earlier. They used to think there was another planet called Vulcan near the sun to make Mercury do this weird thing, and that isn't needed. It's just the strong gravitational field of the sun that makes Mercury's entire orbit precess. So there's a lot of
Interesting.
interesting things going on in those fields that close to the sun.
Fascinating.
Yeah, yeah.
Oh, cool.
Yeah.
All
So
right.
then Einstein to the
What's the other
rescue
question?
again.
Next question I've got is how can there be ice on Jupiter if it's so warm?
Yeah.
So I don't actually know the temperature of Jupiter. I know it's hot,
Hmm.
but we do see ice at the the poles,
Well, some at Jupiter
right?
isn't that warm, I think.
Yes, exactly.
Further up in the
But
atmosphere, I think it's pretty cold. It gets warmer
mhm,
when you go further down into Jupiter, like when that
mhm,
comet hit in 1994. But I
mhm.
think the atmosphere is actually not, it's pretty far from the sun. I think it's colder than the Earth.
Yeah. Well, so I think there's something unique going on with Jupiter in that the pressure on Jupiter is high enough. And so if you look at like the phase diagram for water, for example,
Hmm.
you can also look up ones for methane and ammonia. I think
Hmm.
that's probably what we're seeing
Yeah, it's
on
mostly what it is.
on
Yeah.
Jupiter. Hmm.
Mhm.
High and low are kind of relative, so you could have low temperature, um, but that might mean you know it could be hot if the pressure is high enough.
Yeah.
And so basically, there's a lot of very high pressure. You won't burn your hands on a block of ice. Your hands would actually be crushed beyond recognition
Mm-hmm.
because of that pressure. And
Mm-hmm.
so it's like the pressure is compressing all of those gases into
Yeah.
solid,
Right. Because at the cloud
basically.
top, it's actually minus 280 degrees Fahrenheit.
There you go.
Yeah. That's the cloud top. But as you said, when you get further down into it, of course, it'll get hotter.
Yep.
And that's just basic physics.
Right.
Yeah.
Right.
Yeah.
So, um, all right. This is my last question.
Mm-hmm.
It's not quite a specific astronomy question, but
Mm-hmm.
it is kind of related. It is. I thought it was very interesting. So, do heavily forested regions, kind of like Maine, um, do we experience a noticeable difference in oxygen levels or air quality during winter months when all of our trees lose their leaves?
Yes.
Because,
I think we
our,
do, but if you can give a more detailed answer of that.
yeah.
Yeah.
Yeah. So actually there's a really good map, and I can link to this on our Twitter if you follow us. But it shows modeled atmospheric levels of CO2 from satellite and ground measurements taken throughout the year. And so you can see, for example, humans emitting CO2, and then forested regions actually sucking all that CO2 back up. And then if it's winter in the hemisphere, then the CO2 just basically swirl around in the atmosphere until about springtime.
Hmm.
And we actually see the same phenomena with other gases. They also show these kind of seasonal patterns as well.
Mm-hmm. And they show daily patterns also, day and night
Yes.
patterns. Yeah.
Yeah, actually, I didn't look
Yeah.
into that one, but
Right.
yes,
Yep.
that's
Yeah.
true because actually, oceans cycle more carbon than plants do. I think oceans cycle about 40 to 50% of all of our man-made carbon dioxide, while plants only absorb about 25%.
Mm-hmm.
So I don't necessarily think that that means that air quality is worse. I do actually. Well, actually, there's probably some truth to that. But then we have more humidity in the summer,
Mm-hmm.
which traps gases in different ways.
Yeah.
Um, but so, anyways, ocean oceans, like I said, they absorb carbon. They they keep it out of the atmosphere for much longer as well. And so some of that kind of can be locked into kind of decaying matter long term, which ends up deep in the ocean floor. And so it's interesting because that carbon can sometimes take decades or even a millennia to return up to the atmosphere.
Mm-hmm.
Very cool stuff.
Yep.
So that was our FAQ show for you. Hopefully, you learned something different, something new. And we definitely invite you to ask questions to us. Send them to us, WMPG Scientifically Speaking at gmail.com. We love getting questions and trying to answer them. And if we don't know them, we'll find somebody who does. And yeah, you can also just email us or tweet at us, and we'll get an answer to you. So you have been listening to Scientifically Speaking here on WMPG with myself and Bernie. Stay tuned for Something for the Weekend with Anella, and from your favorite nerds, just a reminder to vaccinate, to mitigate, and then we can all congregate. Stay safe.